Hello students, let us now continue with our discussion on derivatives. In my previous video, I had discussed that by derivatives we mean the instantaneous rate of change of one variable with respect to the other. That is, if y equal to fx, then dy by dx is also written as f dash x, and it is the change in the value of y with respect to the change in the value of x, which is x plus h minus x, in the limiting case as h tends to 0. So this we had done in our previous video. Now, then we had also done that in case x is n is an integer, positive, negative, or 0, then we found that derivative of x raised power n, by this principle only, we found it as x raised power n times x raised power of n minus 1. Okay, now let us try out derivative at a point. Now, derivative at a point x equal to a is defined as dy by dx at x equal to a, or we write it as f dash a is limit h tending to 0 f a plus h minus f a over a plus h minus a, which comes out to be limit h tending to 0 f a plus h minus f a upon h. So what we see is, instead of x here, we have a here. Now we can do it directly by applying the value of x as a after finding the derivative. Now here you have to be very careful. Suppose y equal to x raised power n, or which we write it as fx, and if we have to find f dash at, let's say, 2, okay, then we won't first put the value of x as 2 in this. Otherwise, derivative of see, if you first find the value of 2, we get 2 raised by n, which is a constant. Okay, and now when you find the derivative, it becomes derivative of a constant which is 0. But here this is wrong. What we mean is, you first find the derivative at an arbitrary point and then put x equal to 2. So what do we get? It will be equal to n x raised by n minus 1, and then you put x equal to 2. So f dash 2 actually is equal to n into 2 raised by n minus 1 and not 0 as obtained here. So this is a very, very important point, that while finding derivative at a point x equal to a, we first find the derivative at a general point x, and then substitute x equal to a in the value of derivative so obtained. Okay, so let's just quickly do, now this was the direct application. Now suppose we have to do it by the basic principle. So what will we do? Suppose we have to, we are given y equal to, let's say, x square, and we have to find f dash x, or let's say it is fx, at x equal to, let's say, 3. So what will we do? Limit f dash x, first we will find out, will be limit f dash a, or you write it as f dash 3, will be actually equal to limit h tending to 0 f 3 plus h minus f3, means At x equal to 3, you give an increment to x, you get 3 plus h minus 3. And corresponding increment in fx is f3 plus h minus f3. So this gets cancelled. F dash 3 becomes equal to limit h tending to 0. Now what is this? 3 plus h would be x plus, 3 plus h whole square minus 3 square over h. We expand it, we get limit h tending to 0. 3 square, that is 9, plus 2 into 3 into h plus h square minus 3 square, which is 9 upon h. 9 gets cancelled. Now all the terms have at least one power of h which can be taken common. 6 plus h upon h, and this becomes 6 plus 0, which is 6, and which is the same result as obtained directly. So you find y equal to x squared, dy by dx is 2x. At x equal to 3, dy by dx becomes 2 into 3, which is 6. It is the same result as obtained here. Similarly, we see one more thing. Now suppose we have, let's say, y equal to fx equal to, let's say, 4 times x square. Okay, and we have to find dy by dx at x equal to 2. So what we'll do is dy by dx will be equal to limit h tending to 0 f of 2 plus h minus f of 2 upon 2 plus h minus 2. This gets cancelled. We are left with dy by dx equal to limit h tending to 0. Now f of 2 plus h, first of all you will write, it will be 4 of 2 plus h whole squared minus 4 of 2 squared upon h. Let's evaluate it. We get limit h tending to 0 4 times 4 plus 4h plus h squared minus 4 times 4 upon h. This and this gets cancelled, and when you apply, you can take out h common. You are left with 4 plus h upon h. This, in the limiting case, it gets cancelled, and the answer as 4 is 4 into 4 plus 0, which is 16. Okay, now, so if you just observe carefully, you have derivative of 4x square as 8 into x. At x equal to 2, it becomes 8 into 2, which is 16. Okay, similarly, let's find the, if you have sum of two functions, like suppose y is equal to, let's say, x cube plus 4x, suppose. So what do we get? Now dy by dx is equal to, now dy by dx will be equal to limit h tending to 0. Now f of x plus h would be x plus h whole cube plus 4 times x plus h minus x cube plus 4x whole upon h. Now it gets solved to limit h tending to 0. We have x cube plus 3x squared h plus 3xh plus xh square plus h cube plus 4x plus 4h minus x cube minus 4x whole upon h. These get cancelled, and every term which is left, we have at least one h in common which can be taken outside, and we get it as 3x squared plus 3xh plus h cube h squared plus 4 whole upon h. no, it is minus 4, 1 minute, yes, plus 4 upon h. Now this and this gets cancelled. Applying the limits, we get 3x squared plus 0 plus 0 plus 4, and so derivative comes out to be 3x squared plus 4. Now what we observe is, it is the derivative comes out to be derivative of this plus derivative of this. Same way, if it is difference of two functions, we get the same thing. So ultimately we have seen, let's check the algebra of limits. Okay, now algebra of limits, we have seen three results. First says that if we have two functions which are differentiable, okay, let f and or let's write t and s are two differentiable functions, so derivative of t plus s is equal to the sum of the derivatives, as we have seen it. Same way, for difference, we have the difference of two the derivative of difference of two functions is equal to the difference of the derivatives. And as seen in the first example, we have seen that derivative of a constant times some function is equal to the constant times derivative of that function. So these three things we have seen, and so we can generalize it to the derivative of a polynomial. As suppose you are given a polynomial, let's say y is equal to a0 x raised by n plus a1 x raised by n minus 1 and so on plus an x raised by 0. Then the derivative of this will be derivative of this plus derivative of this plus so and so. So you get a0 derivative of x raised by n plus a1 derivative of x raised by n minus 1 and so on. Last term will be 0 because there is so the last but one term is a n minus 1 x, so the last term will be a n minus 1. So this way you can do any and every questions where you have to find the derivative of a polynomial. Thank you.